In the previous video, we brought this question to the viewer's attention, where we ask if we can find an extension of an arbitrary field over which all polynomials in fx split. Now, the answer to this question involves some set theory that needs to be handled specially on its own merit, which is why we wish to postpone its proof to a separate video, but we will still lay down its groundwork now, including the following two definitions. An algebraically closed field is one over which every non-zero polynomial splits. And an algebraic closure is an algebraic extension such that every non-zero polynomial over the ground field, or the base field, splits over the extension E. The use of the term algebraic ensures that E is a minimal such extension of F as satisfies this property. By this we mean this is an algebraic closure, and E doesn't contain it doesn't properly contain an algebraic closure of F other than itself. The next result is interesting as well as useful. It's a characterization of a field being algebraically closed. It basically says that a field E is algebraically closed if it is an algebraic closure of any subfield over which E is algebraic. And that in turn is equivalent to E being just at least one subfield's algebraic closure. Now, the implications 1 implies 2 and 2 implies 3 are obvious to prove, so we will do 3 implies 1. Namely, we will assume E is an algebraic closure of a subfield, say F, and we will take a non-zero polynomial G, and we will prove that G splits over E. Now, by prior discussion, we know that there's a splitting field L of G over E. But then L is algebraic over F because of the transitivity of the algebraic extensions. So that means every element A in L is a root of some non-zero polynomial over F. But then that polynomial must have all roots in E by hypothesis, therefore forcing A to be actually a member of E. Okay, so that means L is equal to E and G splits over E, proving the assertion. Notice that this proof also yields the following equivalence. The algebraically closed, being algebraically closed is equivalent to E having no proper algebraic extension. So in a sense, E is minimal in this case, and in another sense, it's maximal. Meaning, E is if E is algebraically closed, then it is a maximal algebraic extension of itself as well as a minimal extension that is algebraically closed. Okay. We will do the proof of this assertion, that theorem, in a separate video as we indicated earlier. So thanks for listening.